A subtle rise measured in centimeters over years rarely commands public attention, yet the steady movement unfolding beneath South Sister is drawing quiet but persistent scrutiny. How does a volcano shift without erupting? What does it mean when the land lifts, pauses and then lifts again without visible consequence? And how long can such a pattern continue before it signals something more decisive? These are the kinds of questions now circling renewed observations at South Sister, a prominent peak in the Cascade Range, where instruments have recorded a pattern that is neither sudden nor dramatic, but consistent enough to warrant careful tracking. South Sister stands as part of a chain of volcanoes shaped by tectonic forces that stretch along the western edge of North America. Unlike volcanoes that erupt frequently and visibly, this system has drawn attention for a different reason. Over the past several decades, the ground surrounding the volcano has been gradually rising, a process known as uplift. This change is not measured in meters or feet over short periods, but in centimeters and inches over years, detectable only through precise satellite and ground-based monitoring systems. The first clear signs of this uplift emerged in the late 1990s when satellite radar interferometry began revealing subtle changes in elevation across a broad area west of the volcano. What appeared at first as a minor anomaly became more defined as additional data accumulated. By the early 2000s, scientists had measured approximately 13 centimeters or about 5 inches of uplift across an area spanning roughly 20 kilometers or about 12 miles. This was not a localized bulge, but a wide, gentle swelling of the landscape. What made this particularly notable was not just the presence of uplift, but its persistence. The deformation did not occur as a single event. Instead, it unfolded gradually, suggesting that something beneath the surface was steadily changing. The leading interpretation pointed to magma or heated fluids accumulating deep underground at depths estimated between 5 to 7 kilometers or roughly 3 to 4 miles. At these depths, molten rock and pressurized fluids can move and pool without immediately triggering an eruption. Yet the behavior of this system has not followed a simple linear path. Rather than a continuous and uniform rise, the uplift has occurred in pulses. Periods of measurable inflation have been followed by pauses and in some cases slight reversals. This pattern has been observed repeatedly since monitoring began, giving the system a rhythm that resembles cycles of pressure build-up and release. The years between 2020 and 2022 marked a renewed phase of activity within this broader trend. Satellite data and ground-based GPS instruments recorded an acceleration in uplift during this period. Measurements indicated approximately 2.2 centimeters or just under 1 inch of elevation gain between mid-2020 and the following year. While modest in absolute terms, this change was significant in context, representing a noticeable increase compared to the slower rates observed in preceding years. This renewed uplift raised the possibility that fresh material was entering the system from deeper within the Earth. One interpretation suggests that magma was intruding upward, adding pressure to existing reservoirs. Another possibility is that hydrothermal fluids, a mixture of heated water and volcanic gases, were becoming pressurized and contributing to the deformation. Both scenarios point to an active system, though not necessarily one on the verge of eruption. Following this pulse, the period from 2022 through 2025 showed continued uplift, but at a more gradual pace. The deformation did not accelerate further, nor did it show signs of escalating toward a critical threshold. Instead, the pattern appeared to stabilize into a slower, steady rise. This behavior aligns with previous observations, where periods of increased activity are followed by longer intervals of subdued change. The most recent development adds another layer to this pattern. A new episode of deformation began around July 2025, marking the start of another uplift phase. For several months, instruments recorded continued elevation changes consistent with earlier pulses. Then, by mid-January 2026, the movement appeared to stop. The uplift did not reverse sharply, nor did it continue at the same rate. Instead, it entered a pause. This pause is a key detail. In volcanic systems, changes in deformation often reflect shifts in subsurface pressure. When uplift slows or stops, it can indicate that the forces driving the expansion have stabilized or redistributed. In some cases, this may involve a release of pressure, allowing the system to relax slightly. In others, it may signal that magma or fluids have moved to a different part of the subsurface, reducing the upward push on the ground above. Direct evidence of deflation at South Sister has been less pronounced than the uplift itself. However, minor decreases in elevation have been observed at times, consistent with the broader cycle of inflation, plateau, and slight deflation. These changes are subtle, often measured in fractions of a centimeter or small fractions of an inch, but they contribute to the overall picture of a system that is not static. The analogy often used to describe this behavior is that of a reservoir slowly filling and occasionally releasing pressure. Unlike a container that overflows when full, this system appears capable of adjusting internally, redistributing material and pressure without breaching the surface. This capacity for internal balance may explain why significant uplift has not translated into eruption over the past several decades. Seismic activity, another key indicator of volcanic unrest, has remained relatively low in this area. Large swarms of earthquakes, which often precede eruptions by signaling the movement of magma through rock, have not been observed in conjunction with the recent deformation. The absence of such seismic signals suggests that while material may be accumulating at depth, it is not rapidly forcing its way upward through the crust. The current alert level for South Sister remains at normal, with a green status indicating no immediate signs of hazardous activity. This classification reflects the overall assessment that despite ongoing deformation, the system does not exhibit the combination of signals typically associated with an imminent eruption. There are no rapid spikes in uplift, no sustained earthquake swarms, and no significant changes in gas emissions at the surface. At the same time, the classification of South Sister as a very high-threat volcano underscores the importance of continued monitoring. This designation is not based solely on current activity, but also on the volcano's potential impact. Its location within a region that includes populated areas and critical infrastructure means that any future eruption, even if unlikely in the near term, could have significant consequences. The long-term trend observed from the 1990s through the 2020s reveals a system that is persistently active at depth. The cumulative uplift over decades, combined with repeated pulses of deformation, indicates that magma and fluids are being supplied to the subsurface environment. However, the lack of escalation suggests that this material is not reaching the shallow levels typically associated with eruption. This distinction is crucial. Not all magma movement leads to volcanic activity at the surface. In many cases, magma can intrude into the crust and solidify before it has a chance to erupt. Alternatively, it can remain in a semi-molten state, contributing to pressure changes without creating pathways to the surface. The behavior observed at South Sister appears consistent with these scenarios. Monitoring technologies have played a central role in revealing these patterns. Satellite-based systems can detect ground deformation over large areas with remarkable precision, measuring changes of just a few millimeters or a fraction of an inch. Ground-based GPS stations provide continuous data, tracking movement in real time. Together, these tools allow scientists to build a detailed picture of how the Earth is changing, even when those changes are imperceptible to human senses. The combination of long-term data and recent observations provides a framework for understanding the current state of the system. The repeated cycles of uplift and pause suggest a process that is ongoing but not accelerating toward a critical point. Each new pulse adds to the cumulative deformation, but also reinforces the pattern of moderation. As of early 2026, the The pause following the most recent uplift episode stands as the latest chapter in this sequence. Whether this pause will be followed by another period of inflation, a phase of slight deflation, or an extended period of stability remains uncertain. What is clear is that the system continues to evolve beneath the surface, driven by processes that operate on timescales far longer than typical human observation. As the pause observed in mid-January 2026 settles into the broader pattern, attention shifts toward what this temporary stabilization represents within the longer cycle. The absence of continued uplift does not indicate inactivity, but rather a redistribution of forces beneath the surface. In volcanic systems where pressure builds gradually, these pauses often mark a transition point where accumulated stress within underground reservoirs finds pathways to adjust without forcing material upward toward eruption. The deformation recorded over the past several decades suggests that the system beneath South Sister operates with a degree of balance that prevents rapid escalation. Instead of a steady climb toward a critical threshold, the pattern reflects incremental charging, followed by intervals of equilibrium. This behavior points to a subsurface structure that can accommodate new material while maintaining structural integrity. Magma introduced from deeper sources may spread laterally, cool, or mix with existing material before it can concentrate enough energy to fracture overlying rock. This gradual process helps explain why the uplift zone extends across a wide area rather than forming a sharply defined bulge. A deformation field measuring approximately 20 kilometers, or about 12 miles, across indicates that pressure is distributed rather than focused. In systems where magma rises quickly and directly toward the surface, deformation tends to be more localized. Here, the broad uplift suggests a deeper source, with material accumulating in a region that spreads stress outward instead of pushing vertically with intensity. The depth of the inferred source, estimated between 5 to 7 kilometers or roughly 3 to 4 miles, further supports this interpretation. At such depths, the surrounding rock exerts significant pressure, which can contain magma and fluids even as they expand. This containment allows the system to store energy over extended periods without releasing it through eruption. It also means that changes at the surface occur slowly, filtered through layers of crust that absorb and diffuse movement. One of the more notable aspects of the recent observations is the consistency of the pattern across different monitoring methods. Satellite measurements align with GPS data, both indicating similar rates and pauses in deformation. This agreement strengthens confidence in the interpretation that the system is behaving in a stable, repeating manner, rather than exhibiting erratic or unpredictable shifts. When independent measurement systems converge on the same conclusion, the margin for error narrows and the overall picture becomes clearer. The absence of significant seismic activity continues to reinforce this stability. Earthquakes associated with volcanic processes typically occur when magma forces its way through rock, breaking and fracturing it in the process. These events often cluster in swarms, creating a recognizable signal that precedes many eruptions. At South Sister, such patterns have not materialized alongside the deformation. Small, isolated events may occur, as they do in many tectonically active regions, but they have not formed the sustained sequences that would suggest upward migration of magma. Gas emissions, another indicator of volcanic activity, have not shown notable changes either. When magma approaches the surface, dissolved gases begin to escape, often leading to measurable increases in emissions of carbon dioxide, sulfur dioxide, and other compounds. These gases can alter the chemistry of nearby water or create visible plumes. In this case, monitoring has not detected significant deviations from baseline levels, suggesting that any magma present remains sufficiently deep to keep its gases contained. Taken together, these observations form a consistent picture of a system that is active but contained. The cycles of uplift and pause reflect ongoing movement at depth but without the accompanying signals that would indicate a shift toward eruption. This does not eliminate the possibility of future activity, but it does place current conditions within a context of long-term stability rather than immediate change. The designation of South Sister as a very high-threat volcano remains relevant in this context. This classification is based not only on current behavior, but also on historical patterns and potential impact. Past eruptions in the region have demonstrated that even moderate volcanic events can produce significant ashfall, lava flows, and disruptions. The proximity of populated areas and transportation corridors increases the importance of maintaining awareness even during periods of apparent calm. Long-term monitoring provides the foundation for this awareness. By maintaining continuous records of deformation, seismicity, and gas emissions, scientists can identify deviations from established patterns. At South Sister, the baseline now includes decades of uplift interspersed with pauses. Any departure from this rhythm, such as a sudden acceleration in deformation, a sharp increase in earthquake activity, or a noticeable rise in gas output, would stand out clearly against the historical record. The current pause may also offer insight into how pressure is managed within the system. When uplift slows or stops, it suggests that the forces driving expansion have either diminished or been redirected. This could involve the transfer of magma into adjacent areas, where it cools and solidifies, effectively removing pressure from the central reservoir. Alternatively, it may reflect the release of gases from magma at depth, reducing volume without requiring upward movement. These internal adjustments are critical to understanding why some volcanic systems remain quiet despite ongoing activity. The ability to redistribute energy and material prevents the buildup of conditions necessary for eruption. In this sense, the repeated cycles observed at South Sister can be seen as a form of natural regulation, where the system maintains balance through incremental changes rather than dramatic events. However, this balance is not necessarily permanent. Geological processes operate over timescales that extend far beyond decades. What appears stable within a human lifetime may represent only a phase within a longer cycle. The accumulation of magma over centuries could eventually alter the dynamics of the system, creating conditions that differ from those observed today. This possibility underscores the importance of sustained monitoring and analysis, even when immediate risk seems low. The period between 2020 and 2022 demonstrated how quickly the rate of uplift can change within this broader framework. A measurable increase of approximately 2.2 centimeters, or just under 1 inch, over a relatively short interval highlights the system's capacity for variation. While this change did not lead to escalation, it serves as a reminder that the processes at work are not static. Similarly, the onset of the most recent deformation episode in July 2025 shows that new pulses can begin with little warning. The transition from steady conditions to renewed uplift may not be accompanied by dramatic signals, making continuous observation essential. The subsequent pause in January 2026 completes this cycle, reinforcing the pattern but also leaving open the question of what comes next. Will another pulse begin within months, or will the system remain in a prolonged state of equilibrium? Historical data suggests that both scenarios are possible. Previous cycles have varied in duration and intensity, with no fixed schedule governing their occurrence. This variability adds an element of uncertainty, even as the overall pattern remains recognizable. Despite this uncertainty, the absence of escalation provides a measure of reassurance. The indicators that typically precede volcanic eruptions remain absent, and the system continues to behave within established parameters. This does not diminish the significance of the observed activity, but it places it within a context that emphasizes monitoring rather than alarm. The broader implication of these findings extends beyond a single volcano. South Sister serves as an example of how volcanic systems can remain active beneath the surface without producing visible eruptions. The concept of a breathing system, where the land rises and falls in response to internal processes, highlights the complexity of these natural phenomena. It challenges the perception that volcanic activity is defined solely by eruptions, emphasizing instead the continuous interplay of forces that shape the Earth's crust. For those tracking these changes, the focus remains on data and trends. Each new measurement contributes to a growing dataset that spans decades, allowing for increasingly refined interpretations. Advances in technology continue to improve the precision and coverage of monitoring systems, making it possible to detect even smaller changes over larger areas. As this record expands, patterns that were once uncertain become clearer. The cycles of uplift and pause at South Sister are now well documented, providing a framework for understanding future activity. While the exact timing and magnitude of future changes cannot be predicted with certainty, the existing data offers a basis for evaluating what constitutes normal behavior for this system. If you found this video clear and informative, make sure to like, share, and subscribe for more updates on real-world geological activity. Don't forget to tap that hype icon to help this video reach a wider audience and keep more people informed.